Okay, welcome to Introduction to Rational Functions. So first of all, we need to know what is a rational function. And the second thing I need to know is, can I still use this little pad to write this stuff? So rational function is something like f of x equals p of x over q of x. Or p and q, functions p of x and q of x, are polynomials. Okay, so one polynomial might be something like f of x could equal 3 times x plus 1 divided by x plus 2. Okay, since the numerator and denominator are polynomials, these are factors, so we cannot just divide like an x by an x, for instance, here. You have to find a whole factor, x plus 1 or x plus 2. If we have another factor down here like x plus 1, which would make the denominator a quadratic, but now we can cancel this, but very important thing, we need to say this is only true, and we cancel that when x is not equal to, and I'll explain this in a minute, minus 1. So if we have a minus 1 in here, minus 1 plus 1 will give us a 0. Minus 1 plus 1 here will give us a 0. So we'll have 3 times 0 in the numerator over 0 times x plus 2. So we end up with 0 over 0, which is a indeterminate form. Okay, so a couple things I would want to know, or I'd want you to know about these, is what do these things look like? So let's get a new page and draw a couple of these. So if we have a function like f of x equals 1 over x, okay, we need to look first what values are not allowed in the domain. So you should notice that 0 would not be allowed, because then we would end up with f of 0, if 0 were in the domain, would be 1 over 0, which is actually infinity. Okay, so we know if we get a situation like this, we're going to have an asymptote. So when we graph this thing, generally we get a shape that looks something like this. Okay, and so this is an asymptote here that gets closer and closer to plus infinity but never reaches it. This gets closer and closer to minus infinity but never reaches it. Okay, there's also a horizontal asymptote here, which this gets closer and closer to 0 in the negative direction. This gets closer and closer to 0 in the positive direction. Okay, we can have some other shapes. We can have things like an asymptote going up here and one going here. Of course, all this stuff can be shifted all over the plane. Other one you may see sometime would be something like this and something like this. And in between these two, sometimes we'll get a function that comes up like that. So we're going to have some strange curves. We also, in some cases, will have holes in these graphs, and we want to talk a little bit about when we get a hole. So we have something like a little hole right here. So in this case, this function be defined everywhere except for this value of x, whatever happens to be, let's say 1 or something. Okay, so you have to look at what values do not exist on the x-axis. That's called our domain. So in this case, we're at 1, f would not be equal to 1. In this case, x could not be equal to 0. And over here, wherever this is, if this comes down at 2, let's say x cannot be equal to 2. Okay, one more page, and we'll try to wrap this introduction up. So another thing is, when we do get a function, something like f of x equals, let's say x plus 1 over x squared plus 3x plus 2. Okay. What you might notice right away is we don't know where the zeros are of this function, where our divide by zeros would be, which would cause a problem. So to find where those are, since we can't divide by 0, let's keep the x plus 1 in the numerator. You may want to keep these in parentheses to remember that it's a factor. And if we factor the denominator here, we're going to get x, we'll get a plus 2 and a plus 1. And now if we look at this, the x times the x gives us an x squared. We get 2x from the 2 and the x, and a 1x from the 1 and the x. Adding those together gives us 3x, and then 2 times 1 is 2. Okay, now we can clearly see that the domain has to exclude we say x cannot be equal to any values that make the denominator 0. So if x is minus 2, we'll get a 0. So x cannot be equal to minus 2 or minus 1. Okay. And now, so an alternate way, you might look at this and go grab your red pen and say, oh, I can cancel the numerator x plus 1 and x plus 1 here. And then I can simplify this and say f of x does just equal 1 over x plus 2. But we have to put down that x is not equal to, this is only true when x is not equal to minus 1, because our original equation would have, there'd be a break in the graph at both of these points. So it's okay to simplify like this, but you just have to remember to carry along any points that you divided out. And then generally what we'll see most times is if we get a 0 over 0, like we would have in this case, we want to look at the graph on our calculator and see if it's smooth. If it's smooth, it's going to have a hole in the graph, okay? There's a hole in the graph. If it's not smooth, so if it's, you see asymptotes and things like that, we'll know we have asymptotic behavior and we have an asymptote rather than a hole. But remember, whenever you have any number n over 0, where n is not equal to 0, then we know for sure that this will be an asymptote, okay? Because as we get closer and closer to 0 when we're dividing by something, the number gets bigger and bigger. And it can either happen in the positive direction or the negative direction. Thank you.